Now let's look at a case where there is shrinkage when the product passes through the warehouse. So we go back to the one product example of this red brand shipping. Now we are assuming that there is a shrinkage factor of 90%. And that means if 100 units come in and there's a 10% loss, 90% will go out, or 90 units will go out. So how do we model that? So let's first format these. So this is input cell. So we have origin and destination. Okay, and we have the unit cost. So same like before. Let's put a couple of decimal places there. And flow is changing cell. So our capacity is that. So let's give names here. Our capacity is that. Okay. Now total cost, well, let's give names for these. We won't give a name for our capacity. We'll use this common cell. So total cost is some product of flow and unit cost. So that's our objective function. And we want to minimize that. Okay, so now let's set up the constraints here. Align it properly. Okay, so node balance constraint. Okay. The outflow from the origin points, there is no difference there. So sum if origin node and flow minus sum if destination, so what goes out is subtracted, and that should be less than or equal to plant capacity. There is no change in that one. Okay. But when it comes to warehouse, so now we need to be careful because there is shrinkage here. So we have sum if, okay, what is coming in, let's get that first, origin. No, this is what's going out. Or if 4 is the origin, that is going out. So this is what is going out. Okay, this going out will be only 90%. Okay, let's get what's coming in. What if destination, if 4 is the destination, that's the quantity coming in here. And there is a loss, shrinkage loss of 90%. Okay, so which is that? So what is coming in times shrinkage factor, it gives you what's actually have to go out, because the rest of it is lost. So that should be equal to 0. Now inflow, let's take the outflow from here and copy it and change it to an inflow. So now what's coming in gets a plus and what's going out gets a minus. So you get net inflow. And that should be equal to the demand. Now let's align this. Okay, you need to make sure that everything is aligned properly. Okay, so now let's give names for these. We'll just use 0 for required here, so we won't name that. Okay, now let's name total cost. So now we are ready to run solver. Total cost needs to be minimized. Flow, and then the constraints are net outflow for origins, net flow for warehouse adjusted for shrinkage should be 0, and net inflow for customers should be equal to customer demand. And then finally, of course, we have the arc capacity constraint, which is that one. Change it to simplex LP, non-negative, and solve. We have a solution. And we can run solver table by changing the shrinkage factor. Whether it's going to make any difference or not can be checked out.